Hello, Mr. Ryan, right? Okay, so what's graph?
A graph. It's a graph.
Okay, graph is a collection of the vertex and edges, right? G, vertex and edges. So, can you guess what is a connected graph? What's if I say a graph is connected? What does it mean? Anybody? The vertex, yeah. This is the vertex. Eric, any idea? Is this a connected graph? Why is that?
Because 4 isn't.
Yeah, it's not connected, yeah? And how about this one? Is it a connected graph? Yeah? Yeah? This is a connected graph, yeah? And it doesn't have a cycle, yeah? So we can call it a tree, right? Yeah? Directed acyclic graph, okay? It's not, it's not directed, okay? It's undirected, actually, okay? Okay, so today, given a graph which is connected, okay, make sure we understand this. Connected and undirectional graph. Undirected graph. Okay, so this is connected, undirected graph. Connected, you know, I can do, but it has a cycle somehow, yeah? It can have a cycle, yeah? Given this, given a graph. So how do we represent a graph, remember? We have two ways of representing. Which one is the adjacent list, yeah? Ryan, are you alright?
Yeah.
Adjacent list. Another one is adjacent metric, yeah? These are the two ways of represent the graph data structure using the computer. Right? Adjacent list. So look at what's adjacent list. So we can say node 1 links to 2, 3, 4, right? So it links to 2, 3, 4. No. Node 2 links to 1, 6, yeah? So this key, yeah? Alright. Keys are the node. The values are the list of vertex it connects to, right? Yeah. Yeah? Okay, so 3. What should I put here? What should I put here? 3.
It's gonna be 1, 4.
Yeah, that's it. Yeah, you got it, yeah? And then 4 would be 1, 5, right? And then 6 would be 2, okay? So this is called adjacent list, yeah? The key.
How come 4 doesn't have a 3?
Well done. Well, wow, that's a very good spot, yeah? Yeah, you're right. Good job. Adjacent list. The keys are the vertex. The values are the list of the vertex it connects to, okay? Yeah. The adjacent metric. If it's 1, 2, 3, 4, 5, then you'll be like that, okay? So if these, you'll be a metric, yeah? You'll be metric. So adjacent metric. So let's say 1 to 2. So okay, so if this is 1, yeah, 1 to 2, so it connects to 2. 1 to 3, 1 to 3. Okay, 1 to 4 here. 2 to 1, 2 to 1, 2 to 6, 2, 6. Okay, you got it. So look, if this is metric, Mij means if the vertex I is connected to vertex j. Okay, so if it's undirected, so which means that Mij equals Mji. Okay, in a adjacent metric. So what happens if Mij equals Mji in this metric? What happens? If Mij equals Mji, so what does it mean? It's going to be what? It's going to be met with the diagonal, right? Mij, Mji. So it means that it's undirected graph, okay? Because if the vertex 1 goes to 3, also there's a way to go from vertex 3 to vertex 1, okay? Yeah? So today, easy. Given a connected undirected graph, yeah, we're using the adjacent list, for example, and then we're given this any node, for example. We want to clone. What's clone? Clone. What's clone? What's this word? What does it mean? Clone.
Copy.
Okay, so when we talk about copy, we have two kinds of copy. Deep copy or shallow copy. Yeah? Deep copy and shallow copy. we mentioned this before, yeah? What's deep copy? What's shallow copy? What's deep copy? What's shallow copy?
Deep copy is deep copy and shallow copy is shallow copy.
So what's deep and shallow?
Deep is deep and shallow is
Deep, shallow. Yeah? So usually shallow copy is like you just copy the alias. Alias, yeah? Alias. It doesn't actually copy everything. Shallow copy, deep copy copies everything. Yeah? So it makes exactly the same but separate. But shallow copy may not. Yeah? Sometimes it just copies the alias. And then if you multiply, okay, so let's say a list, yeah, A equals 1, 2, 3. If B equals A, this is a shallow copy. Why is that? So it means that, okay, 1, 2, 3, A points to here, and then B equals A, B also points to here, okay? So if I say A0 changes to 0, then B0 also changes to 0 because they all point to the same copy, right? But if I say the deep copy, then I can say B equals A. Remember, we talked about the list comprehension. We put a single column. Or we can use the copy library dot deep copy. Then that's the separate copy. That in that case, A will point to 1, 2, 3. B will also copy another 1, 2, 3. So if you change A 0 to 0, it doesn't affect the value of B, right? Because they are separate, they are different. Right? Am I right? Yes?
Yeah.
Got it? So if I say, okay, Eric, I make a copy of you. Okay, suppose Ryan, you are like exactly the same copy of Eric. Okay, you are two independent copies. Yeah? Got it? You got it? Yeah? Yeah, so
Yes, sir.
you understand, yeah? You understand, yeah? What's the, okay, can you give me an example of the shallow copy? For example, you're standing in front of a mirror. You're standing in front of a mirror. The copy in the mirror is a shallow copy, right? Am I right? Yeah, yeah. Because if I touch you here in the mirror, I also touch the one in the mirror. Yeah? Got it? Yeah, makes sense? But look, if I touch Ryan, I didn't touch you. Right? You are individual. You are deep copy of each other. Okay?
Deep copy.
Okay. So today we're going to deep copy a clone. Clone usually we mean is a deep copy. Okay. We're going to clone a graph. Okay. So remind me, how many ways we can traverse a graph? Usually, you know, or tree. Remember we talk about least agrarian to agrarian from like
99 times.
maybe more than that. What kind of traverser? What kind of
Breakfast search.
way down? Breakfast search, depth search. Yeah, we're going to do this. Okay, so today we're going to focus on depth search,
Okay.
and then tomorrow we're going to do this breakfast search. Okay.
Yeah.
So look. If this graph, we're going to deep copy this using depth search. Okay. Now one, I'm here. Put that one here. This is I copy one. Okay. Then it has a list of vertex connects to. So I will clone each node. Okay. Yeah. I will clone each node, but using the depth search, then I will clone. Maybe I will go for 2 first, and then 6 first. Yeah, and then go back and go to 3, and then go to 4, go to 5. Okay, but since this is undirected, if you have 3, you don't want to go back to 1, right? So in that case, how do we solve this problem? We don't want to revisit. No book. We're done. Using the hash set. Okay, hash set we visited. So that's the one important thing to when we do this depth search and breadth search in the graph. Usually we need a notebook. Yeah, the hash set to remember the vertex we have visited on the right. Otherwise we will going back. Yeah, we're going back in cycles. Yeah, and then it will never end. Alright. Okay, so let's quickly write this and then okay. So how do we define the notebook in Python? there are a few ways, okay? Define, okay, let's say clone graph. Let's say we have a graph. Maybe we just say a vertex, a node, okay? A node. So let's say we want to define a clone here. We're given a node. So we want to, this is the node we are currently want to clone, we want to copy. And we also need to provide a parameter which is the hash notebook, right? So the nodes we can reference once we copy it. Right? So let's say we have a memo, okay? Memo. At the beginning it's a dictionary, empty dictionary. Okay? We can move this memo here. We can move this memo here. It has no problem. We can move it this inside the scope of the local function. That's fine. So if not node, yeah, if the node is empty, we just return no, okay? And then if the node has been visited in memo, then we return memo node, okay? Yeah, look, if this node we have been visited in the memo, we return it. Otherwise, we create a copy. Yeah, we have this cloned copy. Let's say we just say copy. Okay, this is a copy, which is node, and then we are currently copying this node. So node.value. Okay, and then the second parameter is the neighbors, the list of the vertex it connects to adjacent list. Yeah, so at the beginning it's empty. Yeah. Now this is the key part here. Once we have this copy, we need to put it in the visited set. We need to remember it, right? Yeah. Otherwise, you come up. We need to come back again, and then we don't want that, right? So let's say we need to put it in a notebook. Member node equals copy. Okay, we remember it, and then we look. Here we are this node here, and then you have a list of nodes. We copy this node, so now we want to copy which nodes? All the nodes connected to it. Yeah, all the vertices connected to it. So then we can say copy dot, let's say neighbors. Yeah, neighbors. How do you spell neighbors?
NEIG.
HBORS, yeah. BOR or BOUR? I think one is American. Okay, BOUR.
You're doing the American one.
BOUR is English,
Yeah.
British English. BOR is American English. Okay.
Yeah.
Neighbors equals. Then we want to copy all the neighbors. Then we can say clone. Calling this function clone. Yeah, recursionally clone x for x in node of neighbors. Yeah. Okay, this is a trick here, and then return copy, and then we can just return clone node. Okay. Yeah, look. Can we use the cache function? Remember, we when we do this dynamic programming, we usually put a cache here, right? Yeah. If we put a cache here, what does it mean? It actually means that before this function is returning the value, we need to put it in the memo. So basically you'll be putting here, right? Yeah? There's a difference. Look, if we put a cache here, it actually means that moving this line to here before returning. Right? Alright?
Mm.
Then that's a problem. Why is that? Okay, look, there's a problem. So this doesn't work. Why is that? It doesn't work, okay? This doesn't work. So why we need to save it right after we create the node, we allow copying the neighbors, right? So look, we are here means that we have just copied this. We allow copying the neighbors. Then we put it in the visited set or immediately before we copying the neighbors. Yeah? If I move it after, then there will be a problem. There will be problem. Look, if I move this after the copying, after the neighbors are copied, there will be a problem. Can you tell me why? if I move this, move the copy, move the saving move this right after the neighbors. Neighbors are copies. There will be a problem. Why is that? Look. Okay, let's say here, yeah, that's 1, 2, 3. Yeah? Look, I copy 1. Yeah, the neighbors are 2 and 3.
Yeah.
Now, if I haven't saved it, if I wait for 2 and 3 to be copied, cloned, and then I put it in the visited in the memo, then there will be cycle. Why is that? Look, because 2, if you want to copy 2, you need to copy 1 and 3. But look, 1 relies on 2, 2 relies on 1. So that will be a problem. Why is that? I wait for you to finish, and then you again wait for me to finish. So there will be never ending. There will be never ending. Do you get it? Because 1 said, the vertex 1 says, okay, let's copy 2 and 3. And after 2 and 3 are cloned. And I can mark 1 as being seen, being visited. But when it needs to copy 2, then 2 will say, okay, I want to copy 2. Now let's wait until 1 and 3 are finished. But the thing is, the 1 needs to wait for 2, and 2 says, okay, I need to wait for 1. What does it mean?
They're just waiting for nothing.
Yeah, Eric, you said, okay, wait, and Ryan, I wait until you finish the playing game. And Ryan, you say, okay, Eric, I wait until you finish homework. Right? Yeah, and then you say, Eric, you say, okay, I start homework before after I play the game. So there will be cycle. There will be a cycle, right? End of the cycle. Yeah. Okay. So now how to break this cycle? Then I can say, okay, I start to copy 1, right?
Yeah.
Okay, I'm not waiting for 2 and 3, and I say, okay, 1 is visited. It's visited. Even I haven't actually copied the content of 2 and 3. Right? So when 2 is visited, yeah? 2 is visited, and then you check, okay, 1. I check 1, I need 1 to be cloned. But 1 already been marked as visited. So that's okay. It doesn't go back again. So there's no cycle, right? So here we don't use the cache, because using the cache it will be eventually the same as moving this right before the content, the value is returned as this value. Okay? Yeah. Come on. Look at this. What's this? Copy the neighbors equals clone. Which part is the recursion? Can you point it out? Which part is the recursion?
That.
Yeah, clone. Yeah, calling itself clone. Yeah, clone x. What's x? X is in the node neighbors. So I want to clone the neighbors. I want to clone everything in the neighbors. Okay?
Yeah.
Yeah. This. What's this? Depth search or buffer search?
Depth search.
Well done. Yeah, using the recursion. Yeah, depth search. Okay, the time complexity is what?
O(n).
If there are n vertex and m edges, the time complexity is
n.
No.
N plus n.
Yeah, and O(n) plus n. N vertex, m vertex. N vertex, m edges. Okay. Okay. Yeah, that's it. Do some endings.
Oh yeah, baby.
Okay, that's it for today. Bye bye.
Bye.